तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Okay. So, today we shall continue our discussion on the CMOS inverter. Last class we have already seen the structure of a CMOS inverter, which consists of an NMOS transistor and a PMOS transistor as a load, and the gates of the two transistors are shorted at the input. The drains of the two transistors are also shorted. This is a PMOS transistor, so this is the drain. The source of the NMOS transistor is grounded, and the source of the PMOS transistor is connected to the power supply. The output is obtained at this point, which is the common point where the drains of the two transistors are shorted. Okay. So, this is the structure of a CMOS inverter. In today's class, we shall try to obtain the transfer characteristics, input output characteristics of this inverter, and we shall follow our usual procedure, that is the graphical way of obtaining the input output characteristics. So, what we do, what we have done also for other MOS logic circuits, is basically we have to draw the current voltage characteristics of the driver transistor, okay, which is something like this. This is the NMOS transistor characteristics, okay, and then the load transistor characteristics must now be drawn with VDD as the origin. So, this is the VDD point, say. So, this is the origin point, and now we have to draw the characteristics of the load transistor. Okay. Now, the characteristics of the load transistor, I will draw this way. So, you have coming this way. Okay. Now, let us suppose that the threshold voltage of the NMOS transistor VTN, which we call VTN, is equal to 1 volt, and the VTP, which is minus 1 volt. So, let us write like this: modulus of VTP is 1 volt also, okay, and VDD is equal to 5 volts. Let us take this particular case, and these characteristics. So, 1 volt is the threshold voltage. So, let this be for 1 point, let this be for say 1.5 volts, say 2 volts, 2.5, 3, 3.5, and so on. Okay. This is for the NMOS transistor. So, these are the characteristics for the NMOS transistor at gate voltage of 1.5, 2, 2.5, 3, 3.5. Similarly, we have the characteristics for the PMOS transistor. So, this is the characteristics of the PMOS transistor when the gate voltage is minus 1.5 volts. Now, gate to source voltage is minus 1.5 volts. Now, the drain voltage of this, the source voltage of this PMOS transistor is at 5 volts. Okay. That now, if the input volt, if the gate to source voltage has to be minus 1.5 volts, so the input voltage or Vg must be equal to 3.5 volts. So, this characteristics here, okay, is for V input of 3.5 volts. Okay. Now, so next one, okay, the VGS is minus 2 volts, which means that the gate voltage, okay, VGS is going to be minus 2 volts when the gate voltage is 3 volts. So, 3 minus 5 is minus 2 volts. So, this voltage is 3 volts. So, this is what I am writing here is actually the input, this is the input voltages. So, this is 3, then the next characteristic curve here is for 2.5 volts, next curve will be for 2 volts, next curve will be for 1.5 volts and so on. Okay. Now, so these are the different curves. Now, the operating point is going to be basically the intersection of these two curves. Okay. So, now let us draw the input output characteristics. Okay. This is the output characteristics, output voltage, this is the input voltage on the x axis. Okay. Now, when the input voltage is 0 volts say, okay. Now, this characteristic for the NMOS transistor is going to be along the x axis, but because the gate voltage is less than the threshold voltage, and so the input voltage is along this x axis, and the gate to source voltage of the PMOS is minus 5 volts. So, the point of intersection is actually going to be right at VDD. So, when the input voltage is 0, output voltage is VDD. Now, this output voltage will remain at VDD till the input voltage reaches VTN. Okay. When the input voltage increases to VTN, still the NMOS is not carrying any current. So, the characteristics are along the x axis. So, the point of intersection of the two characteristics is again at this point. So, the output voltage is like this. Okay. So, up to VTN, okay, the output voltage remains at VDD. All right. Okay. Now, suppose the input voltage is increased above VTN. What happens is this curve, so say for example, it has gone up to 1.5 volts here. Okay. When it goes up to 1.5 volts here, so this is the curve for the NMOS transistor. For the PMOS transistor, the gate to source voltage is actually minus 3.5 volts. Okay. So, the characteristics is going to be somewhere here. Okay. Okay. So, 1.5 volts here. Okay. So, this is the characteristics for the PMOS transistor. So, the point of intersection again is very close to VDD. Okay. So, as you keep increasing the input voltage, the point of intersection is still very close to VDD. All right. So, 1.5, 2 volts. Okay. So, this is the characteristics for the NMOS transistor. For 2 volts, the PMOS transistor characteristics is here. So, again the point of intersection, all right, is very close to VDD. All right. So, this is 2 volts for the PMOS, this is 2 volts for the NMOS, point of intersection is here. Now, if we increase to 2.5 volts, okay, we find that the NMOS characteristics is this, the PMOS characteristics is this. So, if it was just less than 2.5 volts, the point of intersection would be right here, okay, of the two curves. Now, if it is slightly greater than 2.5 volts, the point of intersection, say suppose if you take the 3 volt curve, okay, the 3 volt curve for the NMOS is here, this one, okay, and the 3 volt curve for the PMOS, okay, is this one. Okay. The point of intersection we see is right here. So, for the 2 volt curve, the point of intersection is here. When the input voltage is 2 volt, the point of intersection is here. That means the output voltage, okay, is very close to VDD. Whereas, when the input voltage, okay, has increased to 3 volts, okay, the point of intersection has shifted here. Okay. So, there is a large drop in the output voltage when the input voltage is changed by a small amount. So, what we observe is that the output goes like this, and then there is a sharp fall. Okay. There is a sharp fall. So, up to this point it falls like this slowly, which we call, let us call this point VA, and then there is a sharp fall. See, what happens is when the input voltage is increasing above VTN, okay, this NMOS transistor is in the saturation region. Okay. The point of, at the point of intersection, the NMOS transistor is in the saturation region, while the PMOS transistor is in the linear region. Okay, at this point, the PMOS transistor is in the linear region of the characteristic. Then we have a region when both the transistors are in the saturation region. So the NMOS curve, if I just draw it like this, it goes like this, whereas the PMOS curve, okay, it goes like this. Okay. So what we see is when we reach that condition, then with both the transistors in saturation, okay, the output voltage falls from here to here. Slight increase in this curve, okay, in the next characteristic, the point of intersection shifts from right here to here. So there is a very large gain in this region of the characteristics when both the transistors are in the saturation. So this region refers to the region, okay, when the output voltage changes from VA to VB, say, okay, when both the transistors are in the saturation region. Now what happens is, after this, okay, when we exceed this, when we keep increasing the input voltage, say if you go to 3 volts, the point of intersection has shifted here. So in this region, 3 volt, this is the characteristics of the NMOS transistor, and for the PMOS transistor, this is the characteristics. So the point of intersection here, we can see that the PMOS is in saturation, but the NMOS at this point of operation is in the linear region. Okay. So this is in the linear region. Now if you increase the input voltage still further, 3.5 volts, this is the characteristics, and this is the for the NMOS, for the PMOS 3.5 volt, this is the characteristics. So at this point, okay, so this is the operating point, which is still further close to 0. And when the input voltage reaches VDD minus VTP, okay, VDD minus VTP, right, this is VDD minus VTP, this is VDD. That means the gate to source voltage is minus VTP. That means that the PMOS transistor actually cuts off. Okay, PMOS transistor is off, this is conducting, so the output voltage will go to 0. Okay, so at this point the output voltage goes to 0, and then this remains 0 till we go to VDD. So basically, if we look at this input output characteristics, well, there are 5 regions. 1, let me call this 1, this region 2, this region 3, this region 4, and then we have another region 5. So there are basically 5 different regions, okay, of this curve. Okay. Now if you look at the different regions, number 1, for the first region, okay, this region V in is less than VTN, okay, which means that the NMOS transistor is off, it is not conducting. The PMOS transistor, however, is conducting, so the output voltage is going to be VDD. Okay. Now if you look at region 2, okay, NMOS transistor has come into conduction. Okay, if you region 2 is say at 1.5 volts, the input the NMOS transistor has come into conduction. Okay, it is so this is the point of intersection, this is the operating point. NMOS transistor is in the saturation region, okay, of operation. The NMOS transistor is in the saturation region, whereas the PMOS transistor is in the linear region of conduction. PMOS, this is a load transistor, is in the linear region of operation. NMOS is in the saturation region. Okay. In region 3, okay, where there is a sharp change, okay, this is the region 3 of the characteristics. When there is a sharp change in the output voltage for a small change in input voltage, then both the PMOS and NMOS transistors are in the saturation region. Okay. This can be seen here. Okay. This is the region 3. So as we increase the voltage, initially we have this is the operating point where the NMOS is in saturation, PMOS in linear, then both are in saturation, this is the region 3, and then if we increase the input voltage still further, okay, what happens is the point of intersection moves here, where the NMOS is in the linear region and the PMOS is in saturation. So this is in this point 4, NMOS linear, PMOS saturation, and number 5th region, okay, where V input is greater than VDD minus VTP, okay, where the NMOS transistor is conducting fully, the PMOS transistor is off, the output voltage V out is equal to 0. Okay. All right. Now, so this is the characteristic of a CMOS inverter. Okay, we see that it is very close to the ideal characteristics of an inverter in the sense that the output voltage is equal to the supply voltage when the input is low. Okay, is equal to VDD, whereas when the input voltage approaches the supply voltage in this region, the output voltage goes to 0. In between, very close to the midpoint of the characteristic, the 0 to VDD, midpoint of 0 to VDD, there is a sharp drop in the output voltage, okay, from very close to VDD to 0. Okay. So, there is a very high gain region of this inverter. All right. So, this is the characteristics of a CMOS inverter, and we see that this is very close to the ideal CV ideal input output characteristics of an inverter. Okay. Now, an important design consideration for this inverter is this voltage, this input voltage here, okay, which let us call this by the logic threshold voltage. Logic threshold voltage in the sense that if you now plot a line, okay, that is where V input is equal to V output, okay, that is basically a line with a slope equal to 1. Okay, along this line always V input is equal to V output. So, this line will most probably cut the characteristics along this region where the output voltage falls very sharply. Okay. So, at this voltage, so at the if we were to find the point in this characteristics where the input voltage is equal to output voltage, it would be along this region. Okay. So, at this input voltage, okay, at this input voltage, okay, the input voltage is equal to output voltage. The logic threshold is defined as that voltage where the input voltage is equal to the output voltage. Now, the importance of the logic threshold is that at any voltage greater, at any input voltage greater than the logic threshold voltage, okay, the output will be less than the logic threshold voltage and vice versa. So, that is an important point voltage for any logic family. And for a good design, this logic threshold voltage should be the equal to VDD by 2, so that the noise margins are almost the same. The high noise margin and the low noise margin are almost the same. So, we should try to find out what this VTL depends on. Okay. Now, in this region of the characteristics, okay, we have already seen that this region 3 here, okay, both the PMOS and the NMOS are in saturation. Okay. Both the PMOS and the NMOS are in saturation. So, in order to find out the logic threshold voltage, we will write down the equations for the two currents, okay, basically the PMOS current and the NMOS current, and they must be the same. Okay. Now, for the NMOS, the current is equal to Kn Vin minus Vtn squared. Okay. This is the current in the saturation. See, both the transistors are in saturation. So, this is the NMOS current, and this is equal to Kp. So, Kp refers to the PMOS transistor, Kn refers to the NMOS transistor. Okay. VGS minus Vt whole square, VGS the modulus of that, the gate to source voltage is actually equal to VDD minus Vin minus VTP squared. Okay. Kp VDD minus Vin minus VTP squared. So, this is the equation, okay, which is satisfied in that region where both the transistors are in saturation. Now, we can solve this equation. Okay. So, what do we get? Vin minus Vtn is equal to Vin minus Vtn is equal to root of Kp by Kn VDD minus Vin minus VTP. Okay. All right. Now, okay, V in. So, can write if we multiply this side with root k n by k p and bring it this way. So, V in into 1 plus root of k n by k p, okay, is equal to V d d minus V t p plus V t n into root k n by k p. Okay. So, V in, okay, or which is this is actually equal to the logic threshold. Okay. So, this is equal to V d d minus V t p plus V t n into root k n by k p divided by 1 plus root of k n by k p. Okay. So, what so this is the expression of the input voltage, okay, at which both the transistors are in saturation. So, we have a sharp fall, and as we said, this is almost this is equal to the usually equal to the logic threshold voltage. Now, if you look at these expressions, okay, and we find that if k n is equal to k p, if k n is equal to k p, okay, this term is going to be root k n by k p will be 1. So, these two terms will cancel. So, this denominator will be 2. So, and of course, if V t n is equal to V t p, okay, if let us say if k n is equal to k p, okay, V in at this point is equal to V d d minus V t p plus V t n divided by 2. So, if V t p is equal to V t n, okay, V in will be V d d by 2. So, if from this we see that if the threshold voltages, okay, of the two transistors are the same, that is V t n is equal to modulus of V t p, then V in is equal to V d d by 2, provided root k n by k p, that is provided root k n by k p is 1, that is k n is equal to k p. Of course, if k n is not equal to k p, which may be the case if we use the k n and k p we know are dependent on the W by L ratios, it is also dependent on mobility. So, since the mobility in the case of NMOS transistor is different from that of a PMOS transistor, mobility for electrons is more than that of holes, okay, k n by k p may not be the same if we use the smallest size transistors for both NMOS and PMOS, in which case this root k n by k p may not be equal to 1. In that case, the threshold voltages of the two transistors may be slightly adjusted, so that we still get V d d by 2. Okay. So, or else what we can do is we can adjust the sizes of the transistors, so that k n is made equal to k p, and so again if V t n is equal to V t p, okay, modulus of V t p, we still get V n is equal to V d d by 2. So, this logic threshold voltage can be adjusted, okay, so that you get V d d by 2, which is the desired voltage. Okay. So, we see that we have for the CMOS inverter we have a characteristics, input output characteristics, which is almost equal to which is very close to the ideal inverter characteristics, and again this logic threshold can be adjusted to the V d d by 2, so that we have almost equal noise margins, and it gives so that again is we get a very good characteristics. All right. Okay. Now, we have also seen in this while we derive this characteristic that there are two regions, okay, where say region 1 and region 5, where there is basically no current flowing in the through the inverter. Okay. If we come back to this inverter circuit, okay, now the current, for a current to flow from the supply to ground, okay, both the transistors must be conducting. So, if any situation one of the transistors is off, is not conducting, then there cannot be a current. Okay, and that situation occurs when the input voltage either is less than the threshold voltage of this NMOS transistor, or the input voltage is increased to a value where the gate to source voltage, okay, of the PMOS transistor is such that the PMOS does not conduct. So, region 1 and region 5 there is no conduction, okay, and usually the CMOS, okay, is in one of these regions, okay, and so there is no power dissipation as such. There is no static power dissipation, okay, because there is no current flowing, okay, because the power will be equal to the current into voltage. So, that is one of the major advantages of CMOS, that is there is no power dissipation, okay, no static power dissipation. Now, but in the other regions, say if we have 2, 3, 4 regions, okay, there is going to be a current flowing, okay, and these regions will the transistor may be in these regions only when there is a the output is changing, okay, from one state to the other, okay, that is in the transition from one state to the other, okay. Otherwise, there is going to be no power dissipation. Now, if we look at these characteristics, okay, and if we plot the current flowing in these regions, we will find that the current is going to be maximum when in the region 3. For example, if we come back to this characteristics, okay, so when the input voltage is 1.5 volts, the point of intersection is at this point. So, what is the current? The current is equal to this value here. Okay. When we go to 2 volts, when the input goes to 2 volts, the point of intersection is somewhere here. So, the current has increased from here to here, all right. 2.5 volts, the point of intersection is here. So, the current has again increased, okay. But when you go to 3 volts, the point of intersection comes here. So, the current, okay, which is the y axis, okay, the point of intersection has reduced, okay. So, it goes up, okay, from 1.5 to 2 to 2.5, and then again it goes down to 3, 3.5, and again it goes to 0. So, and this region 2.5, say around 2.5, where both the transistors are in the saturation, the current is maximum. So, if we plot the current, okay, the current will be something like this. It reaches a maximum at this point, and again it falls to 0, okay. So, the current is 0 on this side, okay, the current is maximum at this point, okay, again the current goes to 0, all right. So, this is the how the current is going to vary in the CMOS inverter. Now, what we are interested is the power dissipation, okay, how to calculate the power dissipation. Of course, when there is in the static condition, we have said that there is no power dissipation because the CMOS will be either in this 1 to 5 condition. But when it is switching or changing state, there is going to be a power dissipation, okay. Now, let us see what is the power dissipation, okay. Now, let us consider again that this inverter has a capacitive load, which is usually the case, in the sense that this capacitance may be the output of this CMOS may be connected to the input of another CMOS, okay, and then this capacitance is basically the input capacitance of this next CMOS, okay. So, since it is a CMOS, we know that the input there is no resistance, the input resistance is extremely high. So, there cannot be a normal current flowing in the normal static condition, but because of the presence of the capacitance, there will be a current flowing which for basically to charge or discharge the capacitance, okay. Now, suppose the input is high, all right, and it makes a transition like this from high to low. What happens is, where is the current flowing? The input voltage, the output voltage was low, it has to go high, okay. The output voltage would go from low to high. So, in order to do that, the output capacitance, so what happens is, when the input goes from high to low, this NMOS transistor is switched off, but the PMOS transistor is turned on. PMOS is conducting, the NMOS is off. So, a current will flow from VDD to through the capacitance, okay. So, basically to charge this output capacitance. So, the output capacitance will get charged, okay, and the output voltage will rise from 0 towards VDD, okay. Now, in the next period, when this input goes from low to high again, okay, what happens is this NMOS turns on and the PMOS turns off. Then what happens is the current flows, this capacitance basically discharges through the NMOS transistor. Okay, so there is no current flowing through the power supply as such. So in one cycle, as you see, okay, what happens is in one transition, okay, there is a current flowing from the power supply, okay, to charge the output capacitance. In that that is when the NMOS is off and the PMOS is on. NMOS turns off, PMOS turns on, okay, the output voltage was low, so a current flows from VDD to charge the output capacitance, okay, the output voltage rises. Okay. Now what happens is during the other transition, then when the input goes from low to high, okay, this NMOS turns on now, PMOS turns off, so this output capacitance is discharged. So in one half of the cycle we see that a current is flowing from the power supply to charge the capacitance, okay. So that is a current flowing through the power supply. The next half, okay, this capacitance is discharged to ground. So there is not a current flowing directly from the power supply to ground, but one half it is the energy is stored in the capacitance, okay, the current flows into the capacitance, and then that capacitance is discharged to ground in the next half cycle. So if you have to calculate the power dissipation, okay, what we do is we will find out the energy transferred during each transition. Okay. The energy transferred E, let us say, will be given by, okay, VDD, okay, then I dt, okay, during the transition time, okay. So 0 to say tau or t, okay, that is the TD, okay, that is the time delay or the time required for the output to charge, okay, that is the energy transferred, okay, to the capacitance, okay. Now I is nothing but C dV dt, current flowing into the capacitance, C dV C, okay, capacitance voltage, okay. So if we substitute here, E is equal to VDD, okay, C dVc 0 to VDD, the capacitance gets charged up to VDD, all right. Now C is a constant, okay. So what we get is equal to C VDD squared, okay. So this is the energy transferred, okay, from the power supply during each switching, okay, during each cycle we can say if the input is changing, okay. So during each cycle, that is the energy transferred, okay, or the energy transferred from the power supply, C VDD squared. Now if the frequency, so if you have an input square wave or, okay, and the frequency is f, okay, the frequency of that input is you have a clock, okay. So if the frequency of the clock is f, okay, that means there will be f such transitions or f such cycles per second, all right. So per second there will be f such events taking place, okay, and since in each event you have an energy transfer of C VDD squared, the total power dissipation can be given as P is equal to C VDD squared into F, all right. So this is the power dissipation of the CMOS inverter, all right, and this power dissipation depends on the frequency, okay. So if the input frequency is high, so the power dissipation will increase. So it is linearly dependent on frequency. So it is actually sort of myth or whatever you call it, that the CMOS power dissipation is very low. In fact, the CMOS will have a large power dissipation if the frequency is very large. It is linearly dependent on frequency. Only thing is that the static power dissipation is 0, okay. That is, if the input is not changing state, okay, the power dissipation is 0. But if there are transitions, okay, then there is going to be a power dissipation which is linearly proportional to the frequency, Okay. So, if as we increase the frequency of CMOS circuits, okay, the clock frequency is increased, the power dissipation also increases. In fact, it is interesting to note that that if you operate CMOS commonly available CMOS logic circuits, logic gates in the market, available in the market at sufficiently high frequencies, the power dissipation may in fact be greater than the LSTTL, for example. All right. So, if you for example, if you the clock frequency is increased above 5 megahertz or so, it has been shown that some of these CMOS gates, okay, has a larger power dissipation than the LSTTL gates. So, it is sort of myth to say that CMOS power dissipation is very extremely small, but of course, it is true that actually the static power dissipation is basically a wastage of power. Okay, you are not doing anything. So, in the CMOS, that way it is very efficient in the sense that the power dissipation is not used, is the useful power. The power dissipated is actually useful power in the sense it is used to for switching purpose, and there is no power dissipation when the circuit is not changing state. Okay. Another important thing is that the power dissipation is proportional to VDD squared. Okay. So, this is a matter of concern also in modern VLSI circuits, for example, where as the complexity of the circuits increasing, that means there are more number of gates. So, the power dissipation obviously will go up. This is for one gate. So, if you have more number of gates, there will be more power dissipation. At the same time, the frequency is going up. Okay, circuits with higher and higher frequency are being made. So, the power dissipation goes up. So, the only way to reduce the power dissipation, of course, you can reduce the capacitance. Okay, capacitance is proportional to area. So, if you reduce the area or reduce the dimensions of the individual devices, C will go down. Another way to reduce the power dissipation is reduce the VDD square. This is one of the reasons why, okay, nowadays, okay, the power supply voltages are going down. Okay. Another reason, of course, is because the devices are smaller, we cannot have high voltages because the electric fields will be too high. But one of the reasons is also that the power dissipation has to be reduced. Okay. So, we see that the power dissipation, okay, of a CMOS, okay, is dependent on the frequency. All right. So, we have looked at the static input output characteristics. Okay. We have looked at the power dissipation. The next thing which we shall look at is the propagation delay of this CMOS circuit. Okay. Again, we come back to this diagram of a CMOS inverter. Okay. Now, suppose again we take a transition, all right, that the input goes from low to high suddenly. Okay. The output is going to go from high to low. Okay. The output is going to go from high to low. Basically, what happens is as the input goes from low to high, say 0 to VDD, okay, this output which was at VDD is going to decay towards 0. Okay. Now, what happens is when this input is close to VDD, the NMOS is fully on. Okay. The NMOS is fully on, whereas the PMOS, okay, is off. Okay. Because this is VDD, the gate to source voltage here, okay, is going to be less than is going to be 0 in this case. So, it is going to be off. So, what happens is this capacitance discharges through the NMOS transistor. We can forget about the PMOS transistor now because it is off. So, what we have is the capacitance discharging to the NMOS transistor. When we have the other transition, that is when the output, when the input goes from high to low, the output will go from low to high. Okay. What happens is the NMOS transistor is off. Okay. The NMOS transistor is off, the PMOS transistor is on, that discharges the capacitance. So, when the switching, when you have the input varying like this, okay, one of the transistors is only conducting. So, when the output is falling, okay, that is the output, the capacitance discharging, the NMOS is on, the PMOS is off. So, you can consider only the NMOS transistor. On the other hand, when the input falls to 0, the NMOS is off, the PMOS is on, the output capacitance gets charged. So, we can only consider, we need only consider the PMOS transistor, and we can neglect the NMOS transistor. We need not consider the NMOS transistor during this period. Okay. Now, how do you consider calculate the times? Okay. Now, let us first consider the fall time. Okay. Fall time is the time when the output is falling. Okay, that is this region. Okay, so we have we are considering this case, that is the input has increased from 0 to VDD, say, and the output is falling from VDD to ground. So, as the input has gone up, okay, the NMOS transistor turns on, and that is basically discharging the capacitance. The current flowing through the NMOS has to be considered to consider the discharge. Okay. Now, we know that I is equal to C dV dt. Okay. So, this is the load capacitance, say CL. Okay. So, we can write TF, okay, is equal to integral dt, okay, is equal to CL dVc by I, from output is falling from VD, okay, VOH, say output is high, whatever is the output voltage initially, to somewhere VOL. Okay, so low voltage. Okay. So, this is the fall time. Okay. Now, this is CL. So, initially what happens is the input is high, all right. So, this NMOS input is high, output is also high. So, VD the drain voltage VDS might be greater than VGS minus VT. Okay. So, it means that this transistor is in the saturation region, all right. So, this transistor is initially in saturation, and then as the output is falling, okay, the capacitance is discharging, the output is falling, then it comes to the linear region. So, initially the transistor is in the saturation, and then it goes in the linear region. So, we have to consider both these cases. So, first VOH to, say, let us call it VG prime, where VG prime is nothing but VG minus VTN, okay, where VG is the gate voltage, okay, or the input voltage. Okay. So, we have to take dVc I sat, okay, I sat is nothing but Kn Vc, the Vc squared, all right, VGS minus VT whole squared, okay, Kn VGS minus VT whole squared. Okay. Vc is actually the drain voltage also. The voltage across the capacitance is also the drain voltage, drain to source voltage of the MOSFET. Okay. Plus, so you have CL plus VG prime to VOL. So, in this range the capacitance, the MOSFET is in the linear region. So, you have Kn twice Vg prime Vc minus Vc squared. So, this is the equation. Okay. We have to solve this equation, okay, to get the, so this equation has to be solved to get the fall time. Okay. Now, the solution of this equation, I will just write down the solution of this equation. We get the solution as CL by Kn Vg prime, okay, VOH minus Vg prime by Vg prime plus half. So, this is for this part, then this part is half ln, okay, twice Vg prime minus VOL by VOL. Okay. So, once you solve this differential equation, you get a relation like this, CL by Kn Vg prime into VOH minus VG prime by VG prime plus half ln twice VG prime minus VOL by VOL. Okay. So, this is the expression of the fall time, all right. This is the fall time of the waveform, output waveform. Okay. So, the point here is that when you change the input voltage, if there is an instantaneous change, you do not get an instantaneous change at the output, it will take some time because the capacitance has to discharge. Now, we see that of course, for a good circuit this fall time must be as small as possible, we must try to reduce this fall time. Now, we see that the fall time is actually proportional to CL by Kn. Okay. So, CL by Kn is the fall time proportion determines the fall time. Okay. Now, what is this CL? This is the load capacitance. Now, suppose we are considering this inverter driving a similar inverter. Okay. This inverter is driving a similar inverter, then the CL is nothing but the input capacitance of an inverter. Okay. It is the input capacitance of the inverter. So, we can say Cg, where CL is equal to Cg, where Cg is the gate capacitance or the input capacitance of this inverter. Okay. And this input gate capacitance consists of a large number of components. Okay. Okay. But this can be shown to a first approximation that Cg is nothing but Cox. Okay, that is the oxide capacitance per unit area. This is the oxide capacitance per unit area into area. Okay. What is this area? The input area. The input area is if you look at the input of this CMOS, you have an NMOS and a PMOS. So, the total area. So, Cox is nothing but the oxide capacitance, that is epsilon ox by Tox, where Tox is the oxide thickness. Okay, and area is the area of the NMOS and the PMOS. So, this one will be equal to Cox into Wn Ln plus Wp Lp. Okay. So, this the Wn is the width of the NMOS transistor, Ln is the length of the NMOS transistor, Wp is the width of the PMOS transistor, and Lp is the length of the PMOS transistor. So, the Cl in this expression which we have for the fall time. Okay, in this expression the Cl is actually equal to this Cox into Wn Ln plus Wp Lp. Kn is of course we know as half mu Cox W by L. So, both this Cl is dependent on the dimensions of the device, that is W and L of the transistors. K is also dependent on the W and L ratios, it is also dependent on mobility, both of them are dependent on Cox. Cl is also proportional to Cox, K is also proportional to Cox. So, in fact, this ratio is independent of Cox, but it is dependent on the dimensions of the device. So, in the next class what we shall do is we shall find out how the delays depend on the dimensions. In fact, we shall see that the length of the device is much more important for this delay, because if you look at this expression again just okay, the Cl, the load is proportional to L. Okay, it's proportional to L. So, Cl increases with L increase in L, whereas Kn is proportional to W by L. Okay. So, Kn reduces with increase in L. Okay. So, so this is proportional to L, this is inversely proportional to L. So, Cn by Kn will be proportional to L squared. On the other hand, this is proportional to W, Kn is also proportional to W, this is proportional to W by L, this is also proportional to W. So, this ratio is independent of W. So, it is actually the L or the length of the device which is more important, which is very easily understood, because okay, you see that as the widths increase, the capacitance increase, but the W by L ratio increase, which you have larger current, which means that you have larger current. So, you have a larger current to drive a larger capacitance. So, that is no problem. But if the L increases, the capacitance increases, but the current goes down, because the current is proportional to W by L. So, you have a smaller current to drive a larger capacitance, to charge a larger capacitance, smaller current charging a larger capacitance. So, the delay is going to increase. So, it is that we shall take up in the next class the effect of the W by W's and L's, the widths and lengths, okay, on the delays of the CMOS inverter. Thank you.